சொல்லுங்க மேடம். Tell me, madam.
We can start our program, sir.
Okay, madam. Good evening, good afternoon to all the participants who have gathered over here. Now we are starting with the afternoon session of the AACT STTP on the second day. I hope you had all of you had the lunch. So I request the professor cum coordinator of the AASTTP, Dr. Usha Rani, to provide introduction about Dr. G. Uma Madam, Professor Tripoli, College of Engineering, Guindy, Anna University. I hand over the session to Dr. Usha Rani Madam. Thank you.
Thank you, sir. A very good afternoon to all. I welcome Professor Uma Madam, Professor Tripoli Department, College of Engineering, Guindy Campus. Is the eminent professor. I'm really happy to introduce Uma Madam. Even though for her busy schedule, ma'am has accepted to handle the session in our STTP on behalf of our management and on my own behalf. We welcome you, ma'am, and thank you, ma'am, for your acceptance. Ma'am has guided 14 completed, MS 2 completed, journals IEEE, IET, elsewhere 54, H index 17, I-10 index 28, projects power quality enhancement using custom power devices funded by AICTE, positions held HOD Tripoli, CEG campus, professor in charge PG program power electronics and drives, research areas power quality, distributed generation, EV. Today afternoon, ma'am will be handling the topic power quality issues and solutions in distributed generation system. I hand over the session to ma'am. Please, ma'am.
Yes, sir. Thanks, Usha. Good afternoon. Thanks for I wish to thank Dr. P. Usha Rani for inviting me to this FDTP program to give a lecture on power quality issues in distributed generation systems. Thanks for the opportunity. I also wish to thank the management and the other people who have accepted, who has invited me to this FDTP program. Thanks for the opportunity. Okay, let me start with today's presentation. So distributed generation is mainly covers about the solar, wind, and other fuel cells, what are all the natural sources of fuel available, and how this distributed generation is going to influence the power quality. Yeah, okay, so for that, and also one thing I wanted to share as of now is the earlier power system, if you look into the distribution network, it was radial in nature. Okay, so power generation, transmission, and distribution. In the distribution end, we will be consuming the power. But due to the increased use of DERs, distributed energy resources, so the local network, the local distribution network is also becoming active in nature. Okay, so no longer the distribution network is passive. It is going to be active. It is going to act as a source of energy. Okay, now I have considered, for today's presentation, I have considered wind energy conversion systems as one of the, which is one of the DERs. Okay, let me just review the DERs, the different types of WCCs, how it is connected to the grid, and how we can mitigate the power quality issues due to the integration of wind energy conversion systems. Okay, so the wind energy, it's a renewable source of energy. The overview of the presentation is the scenario. So what is the global scenario of the wind energy harvest? How much wind energy, how much power we are going to harness from the wind? So what are the different components of a wind energy conversion system, and different types of turbine, an aerodynamic model, wind generators, where our electrical engineering is going to play a role, and the different types of wind energy conversion system, how their integration is going to influence the power quality. For the time, I have presented 2 case studies. Okay, and 2 or 3. One is a standalone operation, another one is a grid-tied operation of permanent magnet synchronous generator, and the last one is doubly fed induction generator. Okay, these are how these affect the power quality. So the overview of wind energy sectors is in terms of the wind power installed capacity.
Excuse me, ma'am.
Yes,
Ma'am, kindly put the slides in full screen, ma'am.
Okay.
Thank you, ma'am.
Okay. Okay. In terms of the wind power installed capacity, India is ranked 4th in the world after China, US, and Germany, and we have an installed wind capacity of 36.65 gigawatts. Our country has so far. From the data sheet only I have collected the information. So we have an installed wind capacity of 36.65 gigawatt. And within India, the top states where wind energy harvesting is carried out is potential for wind energy harvest is done is Tamil Nadu, Maharashtra, Karnataka, Gujarat, and Rajasthan. Okay, now to the capital cost to install the wind turbine is approximately rupees 5.5 to 6 crore per megawatt. Okay, this is the scenario in India where Tamil Nadu itself contributing to 37% of the wind power generation, and it is number 1 in India. Out of the total capacity, we are contributing 6 from Tamil Nadu itself. We are contributing 6,007 megawatts. We are number 1 state in harnessing the wind energy. Okay. First, it is an elementary, what everyone know, just for the sake of continuation, I am introducing this, how wind energy is harvested, which means that we all know that energy is converted from one form to another form. Therefore, the kinetic energy, the movement of the wind, the kinetic energy in the wind is converted into mechanical energy, and then it is converted into electrical energy. This is the flow diagram. So the what causes the rotation, or what causes the change in the kinetic energy of the wind? It is due to the rotation of the earth, uneven heating of the atmosphere by the sun, and irregularities on the earth's surface. It causes seasonal variations. Okay, due to these seasonal variations, the wind velocity changes, and hence the kinetic energy available in the wind varies. Okay, so this is a simple illustrative block diagram. I'm not going into the in the beginning. It is only an illustrative block diagram how energy conversion is being carried out. So from the wind energy, from the wind turbine, the shaft of the wind turbine is connected to the generator. Then the generated power is conditioned using a power electronic converter. So from the power electronic converter, to suit the transmission voltage levels, or we have different types of power electronic converters available, different power transformers are available. This power transformer acts as a pooling station which collects power from different wind turbines, and it acts as a pool. Then it is from this power transformer, from the output of the power transformer is connected to either to AHV line or connected to the transmission line. Okay. Now the wind flow causes a rotation of the turbine, and due to the aerodynamical nature and the mechanical aspects of the wind turbine, it produces a variable rotation, which is converted into electrical energy by the generator, converter, and it can be connected to a local load or to the grid. The same flow diagram, here it is a mechanical part and this is the electrical aspects. From the generator and the power electronic converter and the load, it forms electrical aspects of the wind energy conversion, and this forms the mechanical aspects of the wind energy conversion system. We have the rotor. This is the rotor. This rotor is connected to the shaft of the generator. A generator is mounted here, which is connected to the shaft of the generator, and we have gearbox for speed variation, and we have a hub and the tower. The tower is for holding the turbine blades. And the transformer, whatever the power generated, whatever the power generated from the generator will be at some voltage, and to suit up the transmission level voltage, we are having a transformer which converts, which matches the voltage profile of the generated voltage with that of the transmission line voltage. Okay. So the wind turbine, it's nothing but a complex electromechanical system with the rotor hub, blades, gearbox and generator. Selection of the wind turbine. The size depends on the demand, location and wind profile, with the prime motive of reduction in price and maximizing the wind energy capture. Okay, it's about the selection of the wind turbine. The turbine rating varies from several kilowatts to megawatts. It is possible to manufacture turbines from few kilowatts to few megawatts. So the rooftop wind turbines, they will generate power in the order of kilowatts, whereas where the wind potential is very high, in the places where we can harvest wind energy to a larger extent, there we can put windmills which can harness megawatt of power. Now wind turbine. In the case of wind turbine, the main parameter is the diameter. Okay, so larger the diameter of the wind turbine, larger the swept area, and the blades start moving. If the blades cover a larger area, then it is possible to harness higher energy. So that's why nowadays the emphasis is being given on turbine with the long blades, so that it can cover a larger area, so that the developed energy or the harnessed energy can be enhanced. Okay, so wind turbines are mainly of two types. They are horizontal axis type. It is a HAWT, H-A-W-T, horizontal axis wind turbine, and the next one is a vertical axis wind turbine. So the vertical axis, it is not quite popular, but in our country, but it is generally the structure of this vertical axis wind turbine is like this. About the axis, the blades will be rotating the other direction. The axis, axis of rotation is vertical. So the wind direction, different types of vertical axis turbines. The blade based upon the wind direction, we have multi-bladed, cupped, screened, and the primary. So we have horizontal axis VAWT, vertical axis wind turbine, and vertical axis wind turbine, and it's different types of blades, different types of blades adopted in the case of vertical axis wind turbine are listed here, are shown here for your understanding. So if you look into the horizontal axis, which is quite popular in our country, you could have seen this wind turbines in many of the places. Okay, so this is the pictorial view of the horizontal axis wind turbine is shown here, which is a commonly used wind turbine in our country. The different blades of the horizontal axis is, we have single bladed, double bladed, 3-bladed, multi-bladed. We are based upon the upwind, downwind, and the end. So we have multi-rotor configuration, rotating blades, the blades for the horizontal axis wind turbine. Because we are not into the mechanical part, I'm just showing it for the sake of to collect the trends. What are the different types of blades used? I'm just showing this picture. Okay. If we compare the horizontal axis, vertical axis, and offshore wind turbines, so vertical axis wind turbines are highly efficient and it requires a less starting torque. Okay. Whereas horizontal axis wind turbines, they are less efficient and they are oriented towards the wind direction. They are oriented towards the wind direction and it requires a high starting torque. Okay. The offshore wind turbines, their features are similar to the horizontal axis wind turbines. Offshore wind turbines, it is also so they are same as the horizontal axis wind turbines. I'll just come in 2 minutes. So the vertical axis wind turbine, the advantages are no yaw mechanism is needed, can capture wind from any direction and can be located near to the ground. That is one of the major advantage. The tower height can be very small. The length of that tower height is not at all a matter in the case of vertical axis. And it can have lower wind startup speeds compared to horizontal axis wind turbines. And we have a low cut-in speed. May be built at locations where taller structures are prohibited, can be mounted on rooftops, hilltops, and ridge lines. So horizontal axis wind turbine, the advantages are the tall tower base allows access to strong wind. It is at a higher level. It is at a somewhat at a higher level compared to the ground. It's not at the ground level. Therefore, the tall tower base. So this helps us to access the stronger wind. Highly efficient and commonly used to generate electricity. And the vertical axis wind turbine disadvantages. Most vertical axis wind turbines have an average decreased efficiency compared to common horizontal axis wind turbine. And we have rotors. In the case of vertical axis, the rotors are located close to the ground, where wind speeds are lower and do not take advantage of higher wind speeds above. So it's suitable for, even if higher wind energy is available, it may not be possible for us to harness that. So horizontal axis wind turbine disadvantages. Massive tower construction is required to support the heavy blades, gearbox, and the generator. And it requires an additional yaw control mechanism to turn the blades towards the direction of the wind. Okay, towards the direction of the wind. That is an additional control we need to exercise in the wind generators. I'll just come in 2 minutes. It requires a braking or yawing device during high winds to stop the turbine from spinning and destroying. So the yaw mechanism, the horizontal axis wind turbine, the yaw mechanism helps to rotate orient the turbine towards the direction of the wind. Additionally, during high wind speeds, we can also cut off the, we can bring the machine, bring the turbine to the standstill condition so that the unit can be protected. Okay, so the rotor, hub, blade, and gearbox. Let us understand what is meant by that. So wind plus rotor blade, they are responsible for the power production, and the pitch drive used to keep the rotational speed of the rotor blades at desired operational range. And there is a gearbox, which is nothing but the gear. Gear is used for speed matching. So the low speed, the low rotational speed of the wind turbine is converted into a higher rotational speed for the machine side, for the generator. So it has gear plus bearings to absorb the vibration. And the range of the rotor speed on the mechanical side, in the wind turbine side, is it generally ranges from 7 to 30 RPM. The rotor speed of the wind turbine, the blades, they will be rotating at the rate of speed of 7 to 30 revolutions per minute. So the gearbox typically used in the ratio of, it is the gearbox steps up the speed. So it is in the range of 1:100 to 150. That is one on the mechanical side. This mechanical speed is converted into 100 to 150 times the to electrical speed. So for a 6-pole generator, rated RPM may be 1000. 4-pole it is 1500. You all know that. And for a 2-pole it is around 3000 RPM. So like that, for comparison, depending upon the type of generator employed on the other side, you can select the gearbox ratio. The rotor speed of the wind turbine is not sufficient to produce electricity, as most generators need the speed in the range of, it's based upon the 2-pole to different types of, based on the number of poles in the machine, the speed range may vary from 1000 to 3000 RPM for in the electrical side. Therefore, the gearbox increases the speed of the generator rotor to 1000 to 3600 RPM to render generator functional. So the mechanical speed varies from 7 to 30 RPM, but the available electrical generators, we have a 2, 4, 6 based upon the poles. The speed, the generator speed varies from 1500 to 1000 to 3000 RPM. So the mechanical speed is is matched to the electrical speed by using a gearbox. The gearbox steps up the speed in this case. Okay. The wind aerodynamic model, air creates two types of aerodynamic force when it flows over any surface. One is the drag force. The drag force is in the same direction of the airflow, and the another one is the lift force, normal, so perpendicular to the direction of the airflow. These two forces are responsible for generating the driving torque. So they are responsible to rotate the turbine blades. So the mechanical power generated, P wind, is a function of the wind velocity. If you look into this, is a nonlinear relationship between P wind and the wind velocity. So P wind is a mechanical power available in the wind is or the turbine power. Mechanical turbine power is related to the wind velocity. So this empirical relationship is nonlinear, and here 0.5 rho pi r is the radius of the turbine, and W is the wind velocity. Okay, so here the different types of, what are the parameters we have used, where rho is the air density, r is the turbine radius, wind speed, and lambda is the tip speed ratio, and beta is the pitch angle, and Cp is the power coefficient. So this Cp, which is a function of lambda and beta, pitch angle and the power coefficient, pitch angle and the tip speed ratio. So this is you can find out what is Cp. The power coefficient Cp is around 0.59. Maximum is mathematically, but in practice it will be a little less. The power coefficient will be less only, less than 0.59. So okay, the turbine mechanical torque. This is the turbine mechanical power. The turbine mechanical torque is given by the same expression divided by omega r. Omega r is a rotational speed. Tau into omega is the power mechanical torque. Okay, this is the relationship between the CP lambda and the tip speed ratio for different pitch angles, and we need to find out that approximately you can have the selection for different pitch angle. What is the maximum achievable CP? That's what it is shown here. Okay. Based upon the pitch angle, you can find out what is the maximum CP. Now, if you look into the power, mechanical power versus the wind speed, we have that on the x-axis, the wind speed is divided into four sections, whereas on the y-axis, what is the power generated? Now, as the wind velocity possible is from V cut in to V cut out. Only in this region, from V cut in to V cut out, we can generate the power. Okay, so less than V cut in, the system will be idle, and if for higher wind speeds, when the wind velocity is above the V cut out, higher speed, generation is not possible. Therefore, there is a range of speed over which generation is possible. That range of wind velocity is determined as cut-in speed and cut-out speed. Cut-in is the point at which the generation begins, and cut-out is the wind velocity at which the generation stops. Okay, so less than cut-in or greater than cut-out, no generation is possible. Okay, so between V cut-in and V rated, so the generation, it is like as the speed changes, the power generated also, there is a approximately there is a linear relationship between power generated and the not. I am not telling it is a linear. For increase in the wind velocity, that we can see an increase in the power. But at V rated, beyond V rated wind velocity, there is a saturation between V rated and V cut out. Even though the wind velocity varies, there is a change in the increase in the wind velocity from V rated to V cut out, but there is no appreciable change in the about the mechanical side. Let us move on to the electrical side. So the wind energy turns 2 or 3 propeller like blades around a rotor. That's what the earlier diagrams I have shown. And the rotor is connected to the main shaft. It spins a generator to create electricity. It's a very normal basic understanding only. You all know that. Okay, so generator converts mechanical energy, the rotational energy of the wind turbine, into an electrical energy. So the different types of generator are, we can classify them as synchronous generators and asynchronous generators. As far as electrical side is concerned, synchronous generators and asynchronous generators. Asynchronous generator is nothing but an induction generator. This part, asynchronous, is nothing but an induction generator. We have 2 types of induction machines. One is the cage induction machine, another one is a wound rotor induction machine. So this is the so accordingly we can modify them as cage induction machine, squirrel gauge induction generator, where the gauge induction machine is nothing but with a shorted rotor terminal, like a doubly fed induction generator. It is the rotor terminals are available, the stator terminals are available. You can extract the power or you can feed power in any of them. I will explain this DFIG subsequently. Okay, so DFIG, the induction machine and the induction generator. Asynchronous generator is nothing but an induction generator. Broadly, it has it's a cage induction generator, and we have wound rotor induction generator. So in the parallelly, we have synchronous generators. We have wound rotor synchronous generator. It's a normal conventional doubly excited generator, doubly excited machine. So another one is the permanent magnet synchronous generator, where one is required. Okay, so there is also one more classification of the generators based upon the speed variation. So we have fixed speed turbines and variable speed turbines. So fixed speed turbines, the machines employed for fixed speed wind turbines is nothing but the squirrel gauge induction generator, and it does not require any power converter. So recall the very first block diagram, whatever I have shown. So the use of power electronic converter can be avoided in the case of fixed speed turbines. In the case of variable speed turbines, obviously we have to go for a power converter to interface to match the variable nature of the speed with either to the grid or to the load. So accordingly, to match the variable speed or to harness power for the entire speed entire range of wind generation from V cutout to V from V cut in to V cutout, we have permanent magnet synchronous generators and doubly fed induction generators. Both are we are going to use. So it requires a full capacity power converter. The full capacity power converter in the sense that the kVA rating of the power converter will be approximately equal to the kVA rating of the generator. So that's the meaning of a full capacity power converter. We need to process the entire power generated by the generator. So you require a full capacity, almost the same kilowatt or the kVA level of the converter we have to employ. So that's a major task. And the next one is doubly fed induction generator. So we have on the rotor side. The case of permanent magnet synchronous generator, the converter will be connected on the stator side. The case of doubly fed induction generator, the converter is installed on the rotor side. So, but since the rotor power is only 20 to 30% of the stator power, the converter we are going to put is going to process only a reduced capacity of the total generated power. That's why it is written as reduced capacity power converter. Now, comparison of the wind generators. So the wind generator converts mechanical energy into electrical energy. Over the past 35 years, many generators such as SCIGs, wound rotor induction generators, doubly fed induction generators, permanent magnet synchronous generators, and wound rotor synchronous generators have been developed for wind turbines, by the wind turbine manufacturers. So in an attempt to increase the power density, so power available per unit volume. In an attempt to increase the power density of 10 megawatt class wind turbines, high temperature superconducting synchronous generators have been introduced for the wind energy industry. This is also parallelly recently, I think in yesterday's newspaper or I didn't remember or today. So now it is reported in the article that people have started. There is a reduction in the use of fossil fuels. So the article is quoting that there is a global reduction in the use of fossil fuels, and hence the power industry, they are going for the different types of codes. That's the present scenario. Okay, you can also please go through the article. I remember it's been highlighted in the newspaper. Okay, that's what. Even though parallelly, one part the fossil fuels are decreasing, we are very much aware of that. Parallelly, we are also utilizing the natural resources like wind turbine, like wind energy, solar, hydrogen fuel cells, and so on. Okay, so that's why we are parallelly the attempt to go for a higher power density turbines. The development or research is also going on for the development of high power density wind turbines, particularly in the high power level. It is in the 10 megawatt class. So let us have a comparison or the advantages and disadvantages of each type of generators. So one is the SCIG, which is simple and rugged in construction, squirrel gauge induction generator, lower initial and maintenance cost, and readily available for megawatt applications. It's a very rugged initially, and to begin with, wind energy earlier wind energy harvest was carried out using SCIG. Now the disadvantages of that is it consumes reactive power from the grid. The generator, the reactive power from the grid, and limited to high speed operation only, and it requires a soft starter to limit the inrush current. Okay, The reactive power is a very, very important power, the reactive power. So for the machine, we all know that induction machine can be modeled as a transformer. So to establish the magnetic flux, air gap flux, we require a reactive power. In the case of squirrel gauge induction generator, for the field flux, the air gap flux will be established using the reactive power drawn from the grid. Okay. WRIG, the wound rotor induction generator or double put induction generator. Here the rotor power allows variable speed. Okay, it is possible to have, you all know about what is the synchronous speed. Synchronous speed is nothing but the rated speed of the machine, or depending upon the pole structure, depending upon the number of poles used in the construction of the machine, we have different synchronous. Each machine will have different synchronous speeds. So the synchronous speed, it is possible to have in the case of WRIG, it is possible to have power. It is possible to do the power extraction above and below the synchronous speed. That's why it is mentioned as rotor power allows variable speed, and it has a high starting torque capability and flexible reactive power control. Okay. So, but the initial and the maintenance cost is high. The disadvantage is initial and the maintenance cost is high, and low power factor at light loads. Low power factor at light loads, which means the reactive power, the draw will be large, and hence power factor will be inferior. And slip rings on the rotor side need regular care. Okay. So next, third one is the Pmsc, permanent magnet synchronous generator, which has the rotor has permanent magnets. Okay, the stator is will have a distributed winding, so from where we can generate the power. So high power density and reliability. The advantage is high power density and reliability, and no need for excitation or gearbox. So it can also be used for the direct connection to the rotor of the wind blades. Okay, direct connection, and you can eliminate the gearbox. That is also one of the major advantages of Pmsc. And the lower rotor losses, because the rotor has permanent magnet, and hence no coil or is there, no resistance or anything is there. So it has lower rotor losses, and hence it is a high efficient method of power generation. But it suffers from the disadvantages of high cost for the permanent magnet material. Okay, and the possible demagnetization of the permanent magnets over a period of time. There is a possibility for the demagnetization of the permanent magnets, and the low speed generators are heavy, and the permanent magnet generators used for low speed applications, they are very heavy. And wound rotor, the synchronous generator, the fourth one. It is independent. In the case of wound rotor induction, it is possible to have independent real reactive power control. High torque operation can be achieved, and it also eliminates the need of the gearbox. Okay, but it requires, similar to the Pmsc, it is a high capital and maintenance cost, and requires an additional excitation circuit, and frequent attention is needed for the slip rings. And the last one is high temperature superconducting synchronous generator. It is significantly compact and lightweight, because the aim of the construction is to increase the power density. So obviously, it will have a lightweight and a compact and lower winding losses, and larger air gap eliminates tolerance issues. Disadvantages: high initial cost, cooling system design is complicated, and a greater tendency for rotor speed instability. Okay, what is the grid code requirement for high power wind energy conversion systems? The moment the power is generated, we need to connect it to the, we need to transport the power. We need to send the power for utilization. This channel for transport is via the transmission lines. Okay, so what are the methods by which the wind generators can be connected to an electrical grid? What are the essential parameters to be monitored? Okay, to ensure grid stability and consumer power quality, many specific technical requirements, often called grid codes, have been developed and are regularly updated by the transmission system operators, TSOs, and our distribution system operators. Where at which point you are penetrating into the grid, whether in the transmission line or in the distribution end. Okay, so accordingly, we need to ensure grid stability and consumer power quality. Okay, at the point of interface of the wind electric generator to the grid. So this grid, we can, if it is in the transmission line, it will be taken care of by the TSOs, and if it is on the distribution line, it is taken care of by the DSOs. The main elements in the grid code include the following: grid voltage and frequency tolerance. Okay, active power control, reactive power generation, grid power quality, black start and short circuit capability, and fault right through. Okay, let me read that once again. So the main elements, so the main points during the interconnection of the wind generators to the grid, the variations, the parameters to be monitored are grid voltage and frequency tolerance, active power, reactive power, grid power quality, black start and short circuit capability, and fault right through. The first requirement indicates that the wind energy conversion systems must remain operational. Very important, must remain operational when the grid voltage and frequency varies with the set boundaries or tolerance band limits. So when the wind generator is getting connected to the grid, even if there are variations in the grid voltage during and the frequency variations, then the wind generators should not come out of synchronism, come or pull out from the grid. Okay, it should stay connected with the grid, even if there are any variations in the grid voltage and frequency. The wind generator should stay connected with the grid. That is the first requirement. Second, WECS must control the active power output according to the power command by the transmission system operator or distribution system operator, such that active power curtailment and frequency regulation at the point of common coupling is achieved. So, depending upon the TSO command and the DSO command, it is possible to disconnect few of the turbines or to ensure power quality. Suppose if there are any variations, or if to ensure power quality, it is the WCS must have the capability to control the active power output. That is, by disconnecting some of the wind turbines from the grid, or by pitch control action, you can orient the direction of the turbine in another way where power generation will get limited, will be minimized. Okay, initially what I told was pitch control action was employed for extraction of the maximum power. But for active power curtailment, you can also use the same pitch control, orient the wind blades in another direction such that power generation can be made less. That is a advantage of this pitch control. The third point is wind energy conversion systems must also be able to control the reactive power such that the voltage and the power factor at the point of common coupling is tightly regulated. That's very important. The voltage profile at the point of interface between the generation and the utility, between the load, active load and the utility, is the power voltage profile can be improved by supplying the reactive power. We can also make the wind energy control WCS to have an active control, of the reactive power at the interface between the wind generator and the grid. Therefore, if the reactive power control is exercised at the interface, then it is possible to do the voltage control of the grid and also the frequency control. Okay, the RPG requirement must be fulfilled. It is very important, must be fulfilled independent of the type of wind energy technology used. So it is very important that the voltage profile at the grid has to be maintained by doing the reactive power control of the WECS. In case the wind turbines cannot produce a required reactive power. Okay, so the first point, out of all the points, reactive power reactive power control at the interface point is a very, very important point. Okay, so in case the wind turbines cannot produce required reactive power, additional war compensation devices like SVC or static synchronous compensator can be employed within the wind farm. Okay, that's that point also we need to. So the reactive power control of the wind turbine generators helps to regulate the grid voltage. That is very important. So WCS should also, because only if it is regulated, only if the voltage is regulated, we can say that even if there are, it's very important, only if the grid voltage is regulated, then only we can say that wind energy conversion systems must remain connected with the grid. Suppose if the grid voltage falls below some set values, or if the grid voltage shoots up above some certain values, there is a possibility that the wind energy conversion system may pull out of the grid. Okay, and reconnection is a major issue. So that's why the reactive power control plays a vital role in the interfacing wind energy conversion systems to the grid. And the fifth point, wind energy conversion system should also provide reactive power during abnormal conditions, like when there are grid faults, to support the grid and assist in the fast recovery of the grid voltage. Okay, that's so reactive power control is a major issue. Once again, I'm strengthening the statement. Reactive power control is a very, very important issue. While it's important point one has to take care while interfacing wind electric generators to the electrical grid. Next one, black start capability indicates the ability of the power generation unit to restore normal operations from shutdown mode without using an external power network. Okay, so it should, the wind turbine system should have its own. It should be self-sustained. It should not require it should not depend on the grid power for region to restore the normal operation. So after a blackout. Okay, next, the third point is, seventh point is short circuit capability indicates the ability of an electrical apparatus to interrupt without being destroyed or causing an electrical arc. This is a general nature of the short circuit capability. W turbine should have a very good short circuit capability. Okay, the last but not the least, FRT, fault right through, indicates the ability of WCS to operate through periods of low or high grid voltage. Okay, last but not the least, this point one has to emphasize, one has to understand thoroughly. Fault right through indicates the ability of wind energy conversion system to operate through the periods of low to high grid voltage, meaning which when there are sag and swells, when the grid voltage is less than 1 per unit or greater than 1 per unit, so it is possible to this very fault right through is a capability of the WCS to stay connected with the grid during the periods of sag and swell. That's very important. Among all the grid codes, as I mentioned, among all the grid codes, fault right through and reactive power control are the major concerns of wind turbine and power converter manufacturers. Okay, so both are interrelated. Fault right through and reactive power control, both are interrelated. So this is the important point one has to understand. Of all the grid codes, fault right through and reactive power control are the main concerns for the wind electric power generation. Let me go in detail about fault right through, FRT. Okay, so grid disturbances such as grid voltages, this fault right through is a problem, is a point for grid connected for grid connected machines, for grid connected generators, wind electric generators. Okay, grid disturbances such as grid voltage, sag, swell might lead to disconnection of large scale wind power generation units, meaning which a 10 megawatt generator, if when it was connected to the grid, it may be transporting 10 megawatt of power, at some normal conditions. Suppose due to some faults in the transmission line or in the other part of the network, if the grid voltage falls, there is a possibility for the 10 megawatt wind turbine to pull out of the, or to come out of the synchronism of that at the PCC. So this sudden disconnection of generation units stimulates the instability of the utility network. Okay, so very important. Even during the requirement of the fault right through is even during abnormal conditions like sag in voltage or swell in voltage in the grid side, it is very important that the generator should stay connected. It should not come out of the grid. Okay. This, suppose if it comes out, it may lead to the instability of the network. Okay, that's why this was given. This is given a very large emphasis. The fault right through requirement is a broad category covering zero voltage right through, low voltage right through, and high voltage right through. There are 3 categories of fault right through. Zero voltage, how long it and the induction generator can remain connected even if the grid voltage is 0. And how long? Second, low voltage right through. How long the induction generator, the wind electric generator will stay connected to the grid? How long? It is about the duration. It is about the duration. How long? For what duration the generator will stay connected to the grid? With the grid voltage is 0, or if the grid voltage is less than the rated voltage, or if it is higher than the rated voltage. Okay, the zero voltage right through and LVRT requirements correspond to grid voltage sags. So this is normally a problem that can occur during grid faults. So the grid voltage becomes 0 in the zero voltage right through profile, and in the LVRT profile the grid voltage becomes 15 to 20% of its nominal value. So the high voltage right through corresponds to the swell condition. So sag or swell is different from under voltage or over voltage. Sag or swell is different from under voltage or over voltage. Therefore, this is an important point where I am not talking about. This is sag is different from under voltage. And swell is also different from under voltage. So this FRT, zero ZBRT, LVRT, and HVRT, they are bothered about the sag and swell conditions. Okay, it is not suitable for under voltage or over voltage. According to the EOIN regulation, it's a standard international regulation, EOIN regulation. The zero voltage right through and HVRT profiles of ZON are shown in the diagram. It may vary from country to country. Okay, so which means that if you look into this diagram, the first one, let us say until at t equal to 0, a fault has been initiated, or fault has occurred. Until then, the voltage is 0.9 per unit. Until then, the grid voltage is 0.9 per unit. Okay, it is allowed, the variation, which means that what is the variation, allowed variation in the grid voltage can work up to 1.9 to 1.1 is a normal operation, where normal operation we can perform. Okay, when the grid voltage falls below 0.9 per unit due to some faults, and suddenly if the voltage goes to 0, and if the zero voltage is maintained for a duration of 0.15 seconds, x-axis is a time in seconds, 0.15 seconds, then it should not go beyond this. So if the zero voltage persists for a duration less than or equal to 0.15 seconds, and afterwards if the grid voltage starts building up with this slope, with this whatever the hatched portion is, the wind generator will stay connected with the grid. The wind generator will stay connected with the grid. Okay, this is this entire portion, the grid, which will, but accidentally, but due to some condition, if the zero voltage level exceeds 0.15, or if it is more than this, or this blue region, generator and the utility may, based upon that and the electricity board, it is up to them to stay connected or wind generator can also implement. And once it goes beyond 1.5 seconds, then the wind generators can be disconnected by using the protective relays. This is about zero voltage and low voltage. This is the duration. Yeah, any variation, even if the grid voltage falls to 0.8, and if it recovers within this duration, within this 1.5 seconds, then it means that it will stay connected. That there is no problem in reconnecting about the connection issue. But if the durations are exceeded, then there is a possibility that the generators may pull out of the grid. Okay, this is about ZVRT and LVRT. Now HVRT, when there is a high voltage. Okay, when the voltage goes above 1.1 and stays for a duration, let's say it goes to initiation of the pulse at t equal to 0, and if the duration of the voltage is above 1.1 for a duration of 0.1 seconds, if the duration is less than 0.1 seconds, then the generator will stay connected. So beyond 0.1 second, it may get disconnected. So it is very important during the grid interconnection, LVRT, how the LVRT improvement capabilities of the induction generators is a separate study. Okay, so one has to know about LVRT or a fault right-through requirement according to the international regulation. We have different countries will have different regulations. So these profiles specify that wind turbines must ride through. That's very important. Must ride through, must stay connected instead of trip off, instead of coming out of the grid. It should stay connected during transmission faults. So during grid voltage sags, the FRT functions should start within 20 milliseconds, within one cycle, when the grid voltage falls below 0.9 per unit, and should provide 1 per unit reactive power. So even the advantage is, even during the grid faults, generation apart from the generation, support of the reactive power is very, very essential. Support of the reactive power is very essential during during this ride-through condition. The wind turbine must be connected to an electrical network if the grid voltage profile is above the zero voltage ride-through limit line. The turbine is allowed to disconnect from the grid. The turbine is allowed to disconnect from the grid if the magnitude of the grid voltage falls below the zero voltage ride-through limit line. For offshore wind farms, the plus or minus dead band, plus or minus 0.1 dead band per unit in dead band is reduced to 0.05 per unit. We are giving a variation of 0.9 to 1.1 as the normal operation in the previous diagram. So the variation in the grid voltage is from 0.9 to 1.1. 0.1 variation is allowed for the onshore. For offshore, it is very limited to 0.05 per unit. During grid voltage swells, the grid voltage swells to 1.2 per unit. The wind energy, that's what I have already explained. The wind energy conversion system must ride through for 0.1 second, must stay connected for 0.1 second. To ensure grid voltage recovery, the wind energy conversion system should absorb 1 reactive power. This is in contrast to the LVRT requirement. In the case of LVRT, when the voltage falls below 0.9 per unit, the wind energy conversion system should support 1 per unit reactive power, should provide. Whereas in the case of HVRT, high voltage right through, it should absorb 1 per unit reactive power. So during this fault condition, it is very, very essential that the wind generators along with the converter should provide or absorb the reactive power, so that the generators will stay connected or will ride through the faults. That is very important. Okay, wind energy conversion systems commercial configurations. The major mechanical and electrical components in wind electrical conversion systems are the wind turbine, gearbox, mechanical speed to torque converter, and so on. And accordingly, they are classified as type 1 which are fixed speed wind energy conversion system with SCIG. It's a squirrel gauge induction generator. Type 2, semi-variable speed wind energy conversion system with the WR with the wound rotor induction generator. Semi-variable speed wind electric conversion systems with the DFIG, and full variable speed wind energy conversion systems with SCIG, PMSG, wound rotor and asynchronous generator, or whatever I have listed. They are brought under the category full variable. And type 5, full variable speed wind energy conversion systems with the wound rotor synchronous generators and mechanical converter, not a power converter. We are using a mechanical converter. Well, let's look into the architecture of each of these configurations. What are the different building blocks of each of these? Major advantages and disadvantages of this configuration of the type 1, or they are provided below. So we have a type 1, it's a fixed speed turbine, which is generators, a squirrel gauge induction generator, and we have a soft starter to limit the inrush current, and directly it is connected to the step-up transformer to the grid. So it does not involve any power converter. So sometimes it may use, as I mentioned earlier, the reactive power support will also made a separate. The arrangement for reactive power support is also made by using the bank, by using the reactive power, by using a bank of capacitors. It's a very simple and rugged power conversion configuration, and low initial and maintenance cost, and an inexpensive soft starter, and reliable operation as no power converters are needed, and lower wind energy conversion efficiency because of 1% of the speed range. Because apart from the synchronous speed, it requires a gearbox. Apart, it can the SCIG will work as a generator. This will work for speeds greater than the synchronous speed. Okay, so we need to, suppose if it is 1500 RPM machine, we need to operate it at a speed higher than 1500. Okay, below the synchronous speed generation is not possible, and above the synchronous speed also void wave speed variation is not allowed. So that's why they are put under the classification fixed speed, and 1% speed variation alone is allowed. Only then, only for that, only in that range generation is possible. Otherwise, it will not generate. Changes in wind speed cause grid frequency and stabilization issues, and the grid faults cause severe stress on the mechanical components of the turbine. Okay, now let us it's a simple flow diagram. Understand that the rotor of the wind turbine is connected to the rotor of the machine. Okay. So whenever the machine starts, whenever the machine starts rotating, for the building up of the power, for building up of the voltage, the machine will draw reactive power from the grid. Okay, so that's why I was mentioning about the reactive power in the previous slide. For building up of the shunt magnetic field, the machine will draw reactive power from the grid, the reactive component. So instead of the machine drawing the entire reactive power from the grid, a portion also can be supplied via this compensator, so that the load on the dependence on the grid can be reduced. So whatever the reactive power needed for the generation of the power, without reactive power, generation is not possible for these machines. Therefore, this reactive power is support. Without this capacitor, the entire reactive power drawing will be from the grid only. So, okay, to reduce the dependence, to reduce the reactive power requirement from the grid, we can also employ shunt power devices. The total reactive power can be met partially from the grid and partially from the static devices. Okay, type 2 wind electric conversion system. The main merits and demerits of this configuration are: 1, and lower stress on wind turbine mechanical components and less effect on grid frequency because of the semi-variable speed operation, and higher initial cost because of the power converter, and higher maintenance cost due to the slip rings, and causes the system to power is lost in the external resistor. It's a loss, and it's a lower reliable. The reliability is less. The system still requires a soft starter and grid side reactive power compensator. Okay, so it is similar to the type 1 system, that's all, but it has a extended speed range. Okay, it also works above the above the synchronous speed, but 10% speed variation is allowed. And another important point is, except in the type 1, we have SCIG here. Here the wound rotor. Here rotor power is also available. Okay, so when the wound rotor induction generator operates above the synchronous speed, type 2 operation is only above the synchronous speed. So because of that, the rotor power, just the slip power. The slip power is conditioned, and it is fed into the external resistor. Or you can also connect a load, some heating type of loads you can connect here, so that power loss, instead of dissipating in a resistor, can be converted into an useful energy. Here also, for the machine to work satisfactorily for building up of the voltage, it requires the machine draws the reactive power from the grid, and to the reactive power dependence again can be curtailed to some extent by supplying the reactive power locally by using the shunt capacitors. Of a partial wind generators. Now here we are employing a full partial scale power converter, both on the rotor side as well as on the stator side. Okay, it is both subsynchronous and supersynchronous operation are possible. Below the rated speed and above the rated speed, both are possible. And when the machine runs above the rated speed, it is similar to the type 2. Okay. Now similar to the type 2, and the rotor power available, the rotor slip power we can convert into DC, and once again it is converted into AC, and you can feed it into the grid. During subsynchronous operation, when the wind speed is less than the synchronous speed of the machine, then in that case the power is available, the voltage and the power is generated power is available on the stator. The slip power, a small amount of slip power will be supplied into the rotor, so that you can have the generation. So during the supersynchronous operation, the rotor power is available. That also we can extract and give it to the grid. During subsynchronous operation, whatever the rotor power, the negative slip power, that we can supply using the same bidirectional rotor side converter and the grid side converter. So you can inject into the rotor for a reliable operation for power generation. Here the FRT compliance is complicated because of the direct grid connected DFIG stator terminals and the partial use of the partial rated converters. Okay. The last, the type 4 configuration, the significant pros and cons of this configuration are high energy yield and no stress on mechanical components because of full variable speed. And it is possible to have independent active and reactive power control. And hence which is possible to have excellent fault right-through compliance. It offers an excellent fault right-through capability. The generator is fully decoupled. From the grid because we have one machine side converter, Pmsc, machine side converter, and one grid side converter. So, and hence a full rated power converter comes between the grid and the machine, and hence the machine is completely decoupled, and the FRT requirement of the grid is completely taken care of by the converters. Okay, high power losses in the converter because will degrade the system efficiency, and hence the complexity of the control system for the control of the converter, because we have two converters, machine side converter, and both the converters are processing the full power, and hence the control and of the converters becomes complex. Control and maintenance of the converters is also one of the factors one need to consider. And the type 5 wind energy conversion system configuration, the main features of this are similar to type 4. Wind energy conversion efficiency is high because of the full speed range. We have a separate speed to torque converter. That's what I mentioned about the mechanical converter in the previous slide. So otherwise, conversion of this is converting a variable speed into a fixed speed is done by the speed to torque converter, and hence it is given to the wound rotor synchronous generator. The speed is made constant, and hence the rotor excitation is provided here, and it's similar to a synchronous generator pulse function. Whatever we have discussed so far, different 5 types of wind electric generators, type 1, type 2, type 3, and they are compared like this. You can have a look into this after some time because we are running short of time, and I'll give this slide so that you can pause. The students can, the participants can refer afterwards. Now we'll move on to fixed speed wind energy conversion system. Rotational speed is determined by the grid frequency and the number of poles of the stator winding. Rotational speed of the machine is determined by the grid frequency, so 120 f/p. Okay, the speed variation is within 1% of the rated speed, and hence it is called fixed speed wind turbine. Gearbox is required to match the speed difference between the turbine and generator such that the generator delivers rated power at rated speed. It can deliver rated power only at certain wind speed. It can deliver rated power only at certain wind speed. And this method does not employ any power converter. Generally, it will employ a 3-phase capacitor bank for reactive power support of the machine. Okay, and power delivered to the grid fluctuates with variation in wind speed. When the wind power varies, the active power supplied to the grid also varies. In the case of variable speed wind energy conversion system, it requires a grid gearbox to adjust the mechanical speed with the speed of the generator. So it also helps to reduce the mechanical stress and thereby helps to increase the energy conversion efficiency. Uses power converters, which helps to provide grid side reactive power control, or for the grid to provide reactive power support to the grid. The next one is a permanent magnet synchronous generator. It is a gearless direct drive. So gearless direct drive, which is also one of the advantages, but it processes the entire power via a power converter, which is okay. Magnetic field in the permanent magnet synchronous generator is produced by a permanent magnet. It's a self-excitation. Okay, only the magnets are mounted on the rotor side. We have different configurations accordingly. We have different types of permanent magnet synchronous generator. Okay, therefore it is called self-excited. So excitation is done by the excitation is provided by the permanent magnets. Pmsc can be run with or without gear, but predominantly it is adopted only for its gearless operation. So, okay, power of a gearless Pmsc wind turbine system can be enhanced with using multiple number of poles. Make a large machine with more number of machine, we can increase the speed of the machine. We can have a more number of poles. This arrangement can be directly connected to the grid without the gearbox. Hence, minimizing the mechanical loss, reducing the construction, maintenance, and operation cost of the wind turbine generator system. Okay. Gearless, relatively lower weight and small size, useful in low power wind energy applications. So that's a Pmsc rooftop applications. We can employ this Pmsc based wind power applications, wind energy systems. So advantages, the absence of gearbox increases the system efficiency and reliability. And the disadvantages, it requires more number of poles to match the speed of the gearless wind turbine with that of the wind turbine with the gear, making the direct drive generator larger and heavier. That's all. The research scope is indirect drive synchronous generator with a lesser number of poles one can try. And the parallel research is also going on doubly with the different rotor configurations and with the different permanent magnets. That analysis is also parallelly going on. The next one is the induction generator. Simple operation, brushless structure, good dynamic response, and less price. IG needs reactive power to be fed to generate a magnetic field. Okay, that's what I told earlier. Grid-tied induction generator draws reactive power from the grid. Draws reactive power from the grid in standalone operation, which is not a grid-tied operation. This reactive power can be supplied by external sources such as power electronic converter or a capacitor bank. Okay, that comes under the SCIG of self-excited induction generator. On the basis of the rotor, two types of induction generator used as wind turbine generator. One is the wound rotor, another one is the squirrel gauge. Okay, each one has got its own advantages and disadvantages, and the research scope is grid integration issues and the fault right through capability of induction generators tied to the grid. That's a thing one has to focus for IG based wind energy conversion systems. Okay. Now let us move on to the case studies. Whatever we have done in the laboratory. One is a grid connected mode, Pmsc machine connected to a grid via a converter, because a Pmsc machine requires the use of a full rated converter. This full rated converter, the Pmsc produces a permanent magnet synchronous generator, produces a variable speed, variable voltage on this the variable speed machine. So when the speed of the wind when the wind speed varies, the generated voltage on the stator generated voltage in the across the stator terminals will have variable amplitude and variable frequency. Okay, will have the variable amplitude. In the case of Pmsc, when the wind speed varies, the generated voltage will have variable amplitude and variable frequency. So this variable amplitude and variable frequency directly you cannot give it to an AC load. Okay, the voltage, the power has to be conditioned before being given to the load. Therefore, the variable voltage, variable frequency should be converted into constant voltage and constant frequency. Okay, the power can be different, but it produces a constant voltage and constant frequency. So it inevitably uses a power electronic converter in between the generator and the grid. So this converter, we have n types of power converter and different combinations of the power converters. So one such power converter is a matrix converter. It's a direct AC to AC converter. It is possible to control the active and reactive power on both the sides. So that one we have adopted for doing a case study. In the case of a grid-tied operation, the stator is connected to the grid. In the case of standalone operation, stator is connected to the loads. It may be an AC load or a DC heating loads. Okay, this is the block diagram of a permanent magnet generator connected to the grid via a converter. This matrix converter connects the it matches the variable frequency, variable voltage of the permanent magnet to a constant voltage, constant frequency. So and power on the active power on this side is same as the assuming a lossless power converter. Active power on the input side is equal to active power on the output side. This is the mathematical model of the matrix converter. Okay, the matrix converter, like an inverter or a voltage source converter, you can control the power electronic converter using some pulse width modulation algorithm. One such pulse width modulation algorithm is nothing but the Venturi algorithm. It's a popular algorithm used for the matrix converter, and we have this matrix converter has 9 switches arranged in the form of a 3x3 matrix. That's why it is called matrix converter. So for each of the switches, the duties ratio, the calculated for the duty ratios are shown, and hence by controlling this duty ratio, it is possible to control the output voltage. The governing equations, the single phase representation, of the converter of a grid connected system is, so this UL represents the output of the matrix converter, output from the matrix converter, and this represents the this is the matrix this UL represents the converter operation, and this is the UL represents the utility voltage. Okay, so the output of the matrix converter has to be connected to the utility. It cannot be connected directly to the utility. We'll have some feeder via some inductance only we need to connect. So the resistance associated with the inductance is R. Therefore, output of the converter is connected to the utility or to the grid via a feeder. The feeder resistance and inductance are R&D L. This is the single phase representation, and for the accordingly you can do the we have different ABC. In the case of the ABC coordinates, we have per phase equation, one for the A frame, for the A phase, B phase, and C phase. Accordingly, you can write it as supply voltage equal to grid voltage equal to RIL plus L DIL by dt plus the converter voltage or the stator. So these equations for the individual phases they are given. As of now, this you can leave it. Okay. So governing the equations for the DQ coordinates, decoupling the ABC into DQ, you are converting the. So I have written this expression for Q frame, the same 3 ABC to DQ. We have the transformed voltages and the transformed currents in the DQ frame. Okay. Now let us if we employ a decoupled current controller, which means that this is possible to have independent real reactive power control. So the decoupled current controller is nothing but whatever the power generated from the wind turbine, it on the grid side, we can go for a reactive power control. That's why the total power of the PWM total power of the matrix converter, it's not PWM rectifier, the total power of the matrix converter is S into V conjugate. Okay, S into considering the fundamental components, it is S into V conjugate. So output of the matrix converter, when we go for the computation, we are looking into the fundamental components of the voltage and current. So considering the fundamental components of the voltage and current, the apparent power is equal to V into I conjugate, which is nothing but P plus JQ. P plus JQ, and substituting, it is V into I conjugate, V equal to VD plus JVQ, and ID equal to I plus JVQ, and multiplying, we will say VDID plus VQIQ becomes the real component, and VQID and VDIQ, the cross coupling components, becomes a reactive component. And here P and Q can be independently controlled by controlling ID and IQ. Here, for a balanced case, VD will be equal to VM. When you do the transformation of the three-phase balanced voltages into the path transformation, when you substitute in the path transformation, your direct access component is equal to the peak of the line voltage. So that's why I have written VD equal to VM and VQ will be 0. And for a balance, when the voltages are balanced and they are sinusoids, after when these ABC voltages are given to the path transformation, the VD component will be equal to VM and VQ will be 0. So the output of the after passing through a DQ transformation, after performing DQ transformation, your ID, since VQ is 0, S is equal to VD into ID and J equal to VD into IQ. So which means that P, on comparing this equation with this equation, P equal to VDID and Q equal to minus VD and IQ. So with this converter, it is possible to do independent real and reactive power control, because ID component directly controls the power and IQ components directly controls the reactive power. Independent decoupled current controller. So it is the overall block diagram control scheme for control of the real reactive power. Because why I am telling about the real reactive power is, when you look into the grid, when you look into the connection of the converter into the grid, at the grid interface, whatever the active power, if it is on the distribution end, this low power Pmsc is like a rooftop low power Pmsc normally put on the distributed distribution side. In that case, whatever the active power harnessed from the wind turbine, it has to be connected into the grid. So during this interconnection, in this interconnection point, the active power voltage, whatever, so the grid the power injection, we should not disturb the power quality at this interface point. Okay, we should not. The power injected, whatever the power injected, what is power injected? Power, already we know the mechanical power and the electrical power, but on the grid side, the power injected is power, as far as electrical engineers are concerned, power equal to VI cos phi. Okay, active power equal to VI cos phi. So if it is a three-phase system, 3 VI cos phi. V is a phase voltage, I is a line current. So whatever the active power that is injected, now voltage is fixed by the grid. Voltage is fixed. Now whatever the current injected into the grid, whatever the current injected, voltage of the grid into the current into the grid, that is nothing but the active power. Therefore, to have maximum active power or to make the reactive power 0, the current injected into the grid has to be in phase with the grid voltage. So the output of the matrix converter for active power injection, the current injected, the current transferred to the grid should be in phase with the grid voltage. So this is possible by having Q equal to 0. You should not make any reactive power drawal from the grid. Okay, so that's why in the previous example, I mentioned about the real reactive power control or independent ID and IQ control. Now, ID is responsible for active power transport and IQ is responsible for the reactive power. Therefore, independently by controlling ID and IQ, whatever ID is related to the maximum power, related to mechanical power. But whereas if we take Q is nothing but whatever the power, whatever we are going to inject into the grid. So if we look into the block diagram, so let us mention using the voltage, you require some sensors for measuring for the computation. You require the voltage and currents. Therefore, measure the voltages and currents, convert into DQ transformation. Using VD, ID, ABC to DQ, AB current also convert into ABCD into ABC to DQ. You will get VD, VQ, ID, IQ, and calculate the power VD into ID. Reactive power is nothing but VQ into VD into IQ. Okay, now you can do this reactive power calculation. Now the overall control mechanism is we will have independent loops for active power and reactive power. So this power P star, this reference power, we can take it either from the mechanical side or electrical side, because this is nothing but the active power available from the machine. Due to the generation, due to the wind electric generation, this P star is being generated. This P star is generated from the wind turbine coming external to the loop. And Q star, it is up to us. It is up to the user. If you want to transfer the power at unity power factor, you can make Q star equal to 0. Okay. Now with this set values, P star is nothing but the reference power set by the mechanical system. Based upon the wind speed, the available active power will vary. That you measure and keep it as the reference power. But the Q reference is nothing but at what angle you want to inject current into the grid, whether it is at unity power factor or less than at an angle less than 0, like that. So accordingly, you can make a Q plus equal to 0 or a few var values. Now after this PI controller and rearrangement, finally you will be getting some voltages. That voltages, after transforming into pulse width modulation, they will control the converter. That's all. They will control the converter, and after control, the currents coming out of the control, they will be in phase with the grid voltage, provided Q plus equal to 0. So this is one converter. Since the variable speed machine requires the use of a full rated power converter, one such power converter is a matrix converter we have employed. That's all. The results we'll discuss. Okay. The first one is the Pmsc output voltages when the wind velocity is 7 meter per second. It's a 7 meter per second. They are the Pmsc output voltages. Okay. Then matrix converter output voltages. The matrix converter from it's a step down converter. If we look into this side, it's a output of the matrix converter is a sinusoidal voltage with a peak value of approximately 60 volts. and this is connected to the grid via an R.M.D. So the matrix converter output currents based upon the grid voltage, the matrix converter currents, it is like a 1 voltage converter voltage, and I have shown the equivalent circuit on the one of the slides. The converter and the machine and the converter and the grid are connected via an RL circuit. Therefore, this is based upon the values of R&DL. The grid side, the machine, the matrix converter output currents is like this. This is the current. They are the currents that are going into the grid. And the real and reactive power, the output after the control, after the closed loop control, the real and reactive power. The reactive power is 0. We are able to transfer power into the grid at unity power factor. Okay. Okay. Next one is self-excited SCIG based wind energy conversion system. This is for a standalone load, self-excited machine induction generator. It is a variable speed. If an induction generator is connected to the grid, it becomes a fixed speed machine. An induction generator is connected to a standalone load, it becomes a variable speed machine like a DC gymnastics. So this setup is an isolated induction generator supplying to a resistive load from a fixed capacitor bank connected. So the capacitor bank supplies some magnetizing current. The machine will have some initial, based upon the past experiment conducted on the machine will have some residual magnetism. So with that residual voltage, the capacitor bank will energize initially. It will start supplying the current. The machine will start rotating slowly, and hence the machine will start generating to the full potential. So that's how the induction generator works. So initially in the existing setup, fixed capacitor banks are used for self-excitation process. So this self-excitation process, I'll repeat it once again. So due to the residual magnetism present in the machine, initially the capacitor banks will get energized to a very the residual voltage will be available. That voltage the capacitors will get energized. So when the machine starts moving slowly, when the mechanical input is given, the whatever the stored energy, the energy in the capacitor, it will supply a small amount of reactive power. So when the machine draws reactive power, hello? When the machine draws a reactive power, further it starts building up the EMF. When the machine further builds EMF, the capacitor voltage further increases. It's a one-to-one arrangement, and slowly the machine will start building the EMF to the rated value. So for the proper buildup of the voltage by the induction generator, it depends mainly on the value of the capacitance, value of the suitable size of the capacitor banks must be designed. So you can recall this equivalent circuit of the induction machine. We all know that it is equivalent to a transformer. So for the building up of the shunt magnetic field, we require the capacitor, we require the capacitance. So we have used once again a DQ modeling of the machine, the standard stationary reference frame model of the induction machine available in the textbook we have adopted. So let us go for the modeling of the excitation capacitance. So here the reduced steady state model of the induction generator is shown here. So we have the ID component, the stator reactive current required to generate IG. Required to generate the required for excitation is IDS equal to omega C into VQS, where VQS is the quadrature axis stator voltage and C is the excitation capacitance and omega is a synchronous speed. Then VQS equal to omega lambda ds, omega LM into IDS. These are all some standard, whatever you know only I am just describing, but only thing is IDS, the stator reactive current required for generation is IDS equal to omega C into VQS. Okay, so by plotting the magnetizing current IM versus the generated voltage, and also on the other side we have the magnetizing reactance XM, it is possible to calculate the capacitance needed for the machine, whatever it is available in the lab. It is based on this trial run based upon the plot between magnetizing current and the generated voltage. We have run we built the machine by having different capacitances, and we measured the magnetizing current drawn by the machine, and a plot has been made. Okay, from this, the optimum capacitance needed for excitation is found to be approximately 58 microfarad. So, okay. For a synchronous speed of 1500 RPM, the Xm value is considered from the unsaturated region in the magnetization characteristic. The of the capacitance is very much essential for the self-isolated induction generator. The Xm value of the magnetizing inductance is found to be around this value. This is based upon the, once again, from the nonlinear relationship between Xm and. So as the magnetizing current is increased, as the magnetizing current is increased, you measure the voltage, measure the stator voltage, and also the magnetizing reactance. Okay, so from which we can compute the value of Lm is again Im square. The plot of Lm is like this. It is based upon the magnetizing current. A nonlinear curve is using a curve fit technique, a nonlinear relationship is built between Im and Lm, from which the optimum value of Lm is found to be 0.1728 Henries. And the Xm value at 50 is considered as, at 50 Hertz is 54.26. From the magnetization characteristic, it is observed that as Im increases, as the magnetizing current increases, Xm varies, the reactance varies. As magnetizing current increases, flux increases linearly and saturates. Flux increases linearly and saturates. Okay, this is a conventional setup. There is a normal induction generator, induction machine which was available in the lab. It was excited via a capacitor bank. So the generated voltages was found to be, it is a mathematical model of the system. It is on using the simulation setup, we got the results like this. And this is the current drawn when the machine was connected to a standalone load. This was the current supplied by the machine. So frequency and the capacitance required. As the speed of the machine increases, the frequency of the generated voltage also increases. As the speed increases, the frequency of the voltage supplied by the generator also increases. And obviously, the requirement of the capacitance also decrease. But the capacitance requirement is vice versa. Since it is a variable speed machine or it is not connected to the grid, I am considering this speed range. As the speed of the machine varies, the requirement for the capacitance decreases, whereas the frequency of the machine increases. It is obvious for known reasons. And if we plot the variation of the generated voltage versus capacitance, as the speed varies, the requirement of the capacitance varies from between 40 microfarad to approximately 90 microfarad. For the speed variations from 1200 to 1800. What I wanted to convey finally is, after all these equations, in the case of a standalone induction generator, for the reactive, a standalone induction generator is a variable speed, variable voltage machine. Okay, but the generation is successful provided if you put a suitable capacitance. If you use a suitable capacitance for the VAR support. Okay, but if you use a fixed capacitance, let us say if I use a fixed capacitance of let us say 60 microfarad, then I can use this, or I can do the generation only at 1500 RPM. Okay, but even if the speed, even if the other speeds are available, I need to use, I have to go for, if the speed varies to 1300, then I have to use an 80 microfarad capacitor. So practically it is not possible to switch the capacitor over the entire range. You can go for one optimum capacitor value, and additional VAR requirement you can supply via some power converter. That's to make you understand, the capacitance requirement varies as the speed varies. But in this is the understanding made from the graph. But so that you can switch on from one to the other bank as the speed varies. So the effective way of supplying the, but if you are not using the correct capacitor, there may not be excitation. So VAR support is very essential, and how we are going to support the VAR, how you are going to provide the total capacitance. So there lies the intelligence. Okay, as the load varies, the capacitor size required for the proper buildup of the voltage also varies. Hence, a fixed capacitor bank cannot be used for varying loads and for varying speeds. So to alleviate this problem, we have gone for another setup where a fixed capacitor bank, the requirement of the cage machine, the VAR requirement of the cage machine is supplied locally by a fixed capacitor bank, and I have divided the total VAR into two components. One is the coarse VAR and the fine VAR requirement. Coarse VAR, bulk, and the additional plus or minus VAR requirement that we can supply it via a converter, via the converter. That's why if you look into this flow diagram, we have a capacitor bank. This capacitor bank takes care of the coarse requirement, coarse VAR requirement of the machine. The additional VAR requirement can be provided via a current controlled voltage source converter. This current controlled voltage, don't bother about the block diagram and all, it's very simple only. Now, the fundamental understanding is the current controlled voltage source converter is a 4-quadrant converter. So you can, it is possible to control this CCVSC. It's nothing but a 3-phase voltage source inverter. That's all. It is called current control voltage source converter since because the control mechanism is on the current. Okay, it's called, that's why the current controlled voltage source converter can be made to operate either as a pure inductor or can be made to operate as a pure capacitor, or it can, or a partial, whatever the power factor or whatever the VAR support, it can be made to supply either the lagging VAR or the leading VAR by proper control of this. So in the case of the modified IG setup, the additional VAR requirement for the cage machine for a standard for isolated loads, it was taken care partially by the capacitor bank and partially by the current controlled voltage source inverter. So the effective control of the current control voltage source inverter was carried out by this algorithm. Okay, you can go through this later. So, but it's only finally on the how effectively we are going to control this CCVSC, so that depending upon the speed, whether we need to, the converter has to supply the lagging VAR or for the leading VAR. And the DC, an infinite DC source was considered instead of being connected to a, okay. With this, I will stop. I'll go to the next topic. Time permits. I'll leave the. So with this, I have introduced about the permanent magnet synchronous Pmsc based power generation and IG based standalone power generation are discussed. And similarly, I have also discussed about one more case study. Due to lack of time, I am unable to present because it will take another a lot of case results I have presented. If there are any doubts so far, you can ask. Are there any doubts?
Participants, kindly pose the questions.
Thank you very much, madam, for your valuable information shared by you. Thank you very much, madam. Very informative session.
Thank you, Usha. I think I'm looking for the questions from the chat box, but
a few minutes.
If anybody is interested, let them ask.
Yes, ma'am. Yes, ma'am.
I'll wait. No problem.
Kindly take water, ma'am. You're continuously taking, ma'am.
Okay.
2 minutes.
Okay, I'll take. Thank you. Okay, doesn't matter, Usha.
Yes, ma'am. Yes, ma'am. Participants, kindly post the questions or you kindly ask madam. Hello.
You can unmute yourself. Okay, so I think some of how
Madam, participant named Rajesh Kumar Patnaik has asked one question.
Yeah. It's a synchronous generator. Yeah, out of all the generators, yes. I have seen the question.
Okay,
see, there are fundamentally two types of generation. This asynchronous generation, another one is the synchronous generation. Mr. Rajesh. So, but synchronous generation is always synchronous generators, alternators. You have studied in your electrical engineering. It's supposed to be the one of the versatile generation mechanisms. Okay, so but a synchronous generator can run only at synchronous speed. It cannot run at other speeds. Therefore, to fully utilize utilize the advantages of the synchronous generator under variable nature, including the variable nature of the wind, we have employed that Block Theorem. I have never used that, but whatever I read in the article, a torque converter, variable speed to constant torque converter was a mechanical converter was installed on the rotor side, so that the machines this will render the machine speed constant. That's what it's shown in the Block Theorem. So bits limit, that's what I have mentioned about the maximum power, maximum limit, because wind energy conversion system, you cannot have the 100% power extraction. Mrs. Anthony, Miss Anthony. So you cannot have the entire range as a power extraction. There is a maximum limit beyond which power extraction is not possible. That's denoted as the bits limit.
Participants, any other questions?
Hi, Kumar sir.
Tell me, madam.
Sir, vote of thanks. Proceed for that, sir.
Thank you, madam. Thank you, Uma madam, for providing a valuable information on the various topics regarding wind energy and wind energy conversion systems and how they are integrated with your DC microgrid. And the session proved to be very useful for various research scholars who had used this platform for gaining an insight into the various things about a wind energy conversion system. I personally thank on behalf of the management and on behalf of the coordinator of this STTP, Usha madam, and on behalf of the Triple department for sparing your time in providing this presentation and clearing various doubts, madam. Thank you.
Thank you very much, madam.
Thank you. I wish to thank Dr. Usha and the coordinator. Thanks for the opportunity, and wish all the participants kindly use this platform, because Dr. Usha has invited people from IITs and other persons. I have seen the brochure. Kindly use this opportunity. I request the participants to effectively use, so that when you are able to get the many information in one slot. So you need not run behind for information. So best wishes, and best wishes to the coordinator and your friend Raj Kumar, I think. Okay, Usha's coordinator. Usha is a coordinator. Dr. Usha is a coordinator, and the person who is assisting coordinator, department faculty. I also wish both of them a very good luck. All the best.
Thank you very much, madam, for your blessings.
Shall I log off, Usha?
Thank you, madam. Yes, ma'am. Yes, ma'am. Thank you, ma'am. Thank you very much.
Okay. Thank you. Thanks, Usha.
Thank you, madam. Thank you,
I'm
madam.
logging off. Thank you. Bye.
Madam Usha, madam, can I put the feedback link?
Thank you. Thank you. Bye.
Stop recording, sir. Stop.